Haskell to play nicely with other programming languages. And I will demonstrate this is systems demonstration. I will demonstrate that at the example of Haskell with Objective-C. Don't worry, you don't have to know Objective-C. And, but this is a general approach. It works for other languages as well. So now imagine you want to write a new client-side app. That's cool. Now, to do that, there are probably a lot of existing frameworks and libraries that you have to call in order to get the job done, especially for a graphical user interface or something similar. But this thing doesn't work, which is annoying. And you may think, oh, in Haskell, that's not hard, right? We've got a foreign function interface. So we'll just use that to do the job. But is this it? Can we go and have coffee? I mean, I haven't had coffee after lunch yet. Unfortunately, no, it's not that easy. And let me explain why. At a little example. So this code, little Haskell function, it gets a string, which is supposed to be a URL. And what do I want it to do? Go off over the network, grab whatever web page is at that URL, and dump it to standard out. Now, on macOS, using the Cocoa framework, that's quite easy because there's a function called string with contents of URL, and that does everything. It handles proxies, really nice. But it's an Objective-C API, so I have to write this stuff too. To wrap it into a function, in an extra file, and call it. Well, maybe that's reasonable, but then, well, I can't call it directly because, well, I have to marshal all this data back and forth, and we need foreign function declarations, and now it gets a bit tiresome, right? I mean, this is one function we are calling. Now imagine you write a real application, and you have to call tons of functions, and you have to write this for every single function. Now you know why there are no client applications in Haskell. Well, actually, well, this is not a new problem, right? And Hackage is full of binding libraries. So libraries which wrap a C API in Haskell. And in order to facilitate this, there are tools. In particular, I've written a tool like that called C2 Haskell, which reads a C header, gets out all the definitions, and tries to generate that boilerplate for you. And that's been used in the development of the GTK binding, which I believe is the most fully fledged GUI binding which is available today. It's actually the only really used one. That's strange. Maybe that already tells us that there's something wrong. But GTK is used for nice things like thread scope. That's a real application. It's really useful. And it needs the GUI. So that's great. The question is, does it scale? Well, let me give you a data point. The GTK C library introduced a new version 3 API in 2011. Do you know when that API was made available through the GTK bindings? 2.5 years later. Now take into account that modern application frameworks are huge compared to GTK. GTK is really a toy. Well, we can't even get that done, so there obviously is no way we can do that for bigger frameworks. So really, bridging libraries are a nice idea, but they don't scale. So now this is not a new problem, right? Interoperability is an old problem. So maybe we can use an old solution. And well, when I was young and going to uni and kind of being an undergrad, with a couple of friends, I wrote a modular 2 development environment. And we had a similar problem. We wanted to, in modular 2, we wanted to make use of the underlying operating system on an Atari ST. And what did we have to do that? Write assembly code. And the assembly code, because we needed this interoperability, we had the modular system allow inline assembly code. And in order to make this nice to use, you could even use this, you don't have to read this code obviously, we even could use the identifiers from modular into that, in that assembly code. That was really nice. So let's do the same for Haskell. It's easy. We just all have to gang up on Simon and make him add a C, C++, Objective-C, and Java frontend into GHC, and we are done. Oh, I'm not sure whether that plan is going to fly, but we've got support. We've got a great meta-programming system, something we didn't have in Modular 2 at the time. In particular, we've got template Haskell, and then we've got Jeff's great support for general quasi-quoting. And that's what we're going to use. So let's get back to our original example. So there's the Haskell code, then there's the Objective-C code, and we'll just mix it all together into one. All right, so now, how do we integrate this Objective-C code? Well, we use quasi-quoting, right? That was the idea. So we use language C quote. It's a library for quasi-quoting C dialects. I've extended that to cover Objective-C, so we can pass this code. All right, but now we need the glue code between Haskell and Objective-C. In particular, the common variables. We use this argument URL string in the Objective-C code. Looks simple, but how is this ever going to work? Well, we've got template Haskell splices, various forms of template Haskell splices to integrate Objective-C code into the Haskell code. In particular, the form which is displayed in this example is for expressions, and it has two components. So first of all, it tells the system which variables we want to communicate from Haskell to Objective-C and what their type is. And then we have some information on how to get the result back. And the nice thing about it, given that splice, the library, language C inline, will generate all that gunk for you. That's nice. All right, so this is a demo. I have to write code, right? Well, I'll spare you watching me type, but I'll at least compile something. Right. So let's go here. Can you read that in the back?
Yeah.
You're good? Okay. So this is the same code, right? This is the same code we just had on the slide. There's a little bit of fluff around it. And that's a module which exports this function dump URL. And we call this from another function which calls it with a URL which happens to be the URL at GitHub where the source code of this program is stored. All right, so let's compile this. GLC does its stuff, and we get an executable inline Objective-C. I can kind of bring that up here. And it goes off over the network, gets the source code, and displays it in the terminal. Yay. All right, that was good. And we can have a look at the output of the thing. So we have test in an Objective-C M. That's the Objective-C file. And you see there's lots of nonsense about Unicode encodings and stuff in there. But the good thing is you don't worry about that. That's the library's problem. I mean, that was the premise of the whole setup, right? Okay, so this is fine. So let's do something a little bit more complicated. One problem which comes up all the time is, of course, that we've got data structures in Haskell which we then want to use in Objective-C. Now, here I've got a little example. I've defined 3 types, in particular one record type called particle, which could be a particle in a kind of embody simulation or something like that. And if we want to use that in the Objective-C code, maybe because we write a visualization front end for an embody simulator, and we want to animate the moving particles, then we have to get at all the particle data in the GUI part of the application, which would be written Objective-C, right? We have to somehow do the marshalling for that. Now, we could do that argument by argument, but that's going to be tedious and it's not, again, not going to scale very well. So language C inline has specific support for that, where we can create custom classes in Objective-C which lazily marshal the components of these fields. Because this is a small one, we could just marshal the whole thing. But generally, often these records are big, and we don't want to marshal all the data. Often we don't even need all the data. To do that more efficiently, we do it in a lazy way. And so Objective-C or Cocoa framework has a design pattern which is called immutable classes. So that's a sort of object which, well, is immutable. You don't update it. That seems like a good fit for a Haskell data structure. So we want to map to that. All right. So let's have a look at the code. Or to be precise, I had another slide. So the code for that is here. So you see we've got the same Haskell definition up here. And then we've got the interesting bit. The splice here is a top-level template Haskell splice called Objective-C record. And what we are saying here is we want a class called particle in Objective-C land, which we map, I'm not very inventive with names here, to the Haskell type particle. For those of you who are not so familiar with template Haskell, the two ticks in front of a type name are a quote. It's like a Lisp, only Haskell. So it quotes the name for us so that we can use in template Haskell. And then in Objective-C, the member variables of a class are called properties. And that's what we define next. We've got 3 properties for the mass, X location, and Y location. So you see we don't marshal the entire record in this case. We just marshal the bits which we would need for visualization. The velocity is irrelevant for that. And then on the right-hand side, we again here you see this is actual Objective-C code, and it's wrapped into a quasi-quotation for Objective-C properties. So it's not that we can quote entire Objective-C programs or entire expressions. We can quote fragments of Objective-C programs, part of declarations. And then the library can stitch that together into an entire class definition in Objective-C. And here on the right-hand side, we have 2 function definitions basically, again quoted so that we can manipulate them, which are the getters and setters to update and read the data structure. Update here, of course, means update in the Haskell sense, meaning we create a copy and update one field. It's not a destructive, not a mutable side-effecting update. Okay, so we've got all this, and then a little bit more declarations to complete the example. And again, this is a module which is used in the main module, where we use another of these Objective-C splices which we've seen in the first example. And then we have 2 lines of Objective-C code. So the first line is Objective-C speak for create a new instance of the class particle, which is the one we've generated, and initialize it with a mass of 1, and there's some default values for the other fields. And then we extract the mass and print that. So the program is really super simple. It's really about showing the mapping of these Haskell records to classes. All right, let's try to use that. Let's try to compile that. So I make, and Haskell does its, GLC does its job. And if I run this program, well, no surprise, it prints the mass. But let's look at the generated code. So you will see the particle.hs is the original Haskell code, which has all this inline Objective-C. And then the underscore Objective-C.h and m are the interface and implementation parts of the class. And we are just going to have a look at the interface, because that's a bit nicer to look at. And this is the interface which was automatically generated. So it's the interface for a new class, which is a subclass of NSObject. In Objective-C, everything has to be a subclass of NSObject. And there are 3 properties. Just the 3 we declared in the Haskell side. And they're all read-only, which makes this an immutable class. And then there are constructor declarations, which are not very nicely printed because really this is not for human consumption, but just for the Objective-C compiler. And to construct new versions of this data structure, but with individual fields replaced. And as I said, the reading of the data from from the Haskell side structure, it happens lazily. And behind the scenes, we use stable pointers and all the normal FFI setup which we are used to from Haskell. All right. So in this way, we can even work with more complex data structures. But it doesn't end here. We can do more. So in order to write a real application, right, we want to use the native tools which are provided for the platform. So in this case, for Cocoa, that would be Xcode. Xcode includes an interface builder, which is a graphical tool to compose GUIs. And so I did that. I composed this little GUI. I mean, this is the Xcode window, but the thing inside, okay, that's the window we composed for our little app. So this little app, what it's supposed to do, is going to link to GHC API, and it's going to give us a little wrapper, Haskell wrapper, inside that Mac interface. So in order to work with that, I won't show you all of the code for that, just give you a little idea of what we are doing here. So here there's some supporting Haskell code, which we can ignore for the moment. But what we are going to do here, we are going to implement an entire class, Objective-C class, inside our Haskell module Inline. That's very important because in a lot of object-oriented GUI frameworks, you have to use subclassing in order to instantiate the classes of the framework for your particular application. So if in your foreign function bridge you can't subclass the framework objects, then you're stuck, right? But we can do that. So we declare, we declare an interface here. So that's the Objective-C speak for the class declaration. And then we have got an implementation. And the implementation here, again, the details are not so important. It's just Objective-C code. But you can see how we call various text views, and we start things, and then we get some interpreter results. But the interesting thing which I want to show is where we actually evaluate something. And because I can't find this, I'm just going to search for it. So we've got this Haskell function, eval expression, and we're going to call this from inside Objective-C. So this is an Objective-C method invocation here, where we just use eval expression. Like that's the Haskell function, we just call it in Objective-C. And then we give it some arguments, including the second argument, sender string value, is another method invocation of Objective-C. So that method invocation will happen, then the result is going to be passed through the FFI to the Haskell function. The Haskell function is going to be called, and the result is going to be marshaled back to Objective-C and used in place of this function invocation. Okay, so you can transparently call back between Haskell and Objective-C in both directions in this setup. And if we do that, then we can, of course, also compile this. It takes a little longer because there are a few modules to compile. And once the system is done with that, we can just start our little application. And it's here, and because it's too small, I will use the accessibility feature of macOS to zoom it up. Okay, so now I can use Haskell in my little app. Okay, I can get types of things. I can even load modules and use those. Okay, it just uses hint transparently. And that's, I mean, the code looks strange, but if you know Objective-C is actually pretty simple. So this is not hard, this is easy. All right, so now the critical question, of course, because I started with scaling, right? The other approaches don't scale. Does that scale? Well, let me close by saying, last Australian summer, that's winter for most of you, I've started teaching my 10-year-old and some of his friends Haskell. Because what's the first programming language a child should learn? Well, you know, you're my friends, we're in the Haskell. And it was a pain, not the Haskell coding, that was fun. setting up for 6 kids on their MacBooks a Haskell environment they could actually use was a pain, major pain. So I decided to write something new. So that's an application which uses all kinds of languages. Well, C++ is a lie. That's a bug in GitHub, I don't know. It uses Haskell, Swift, Objective-C all together using this inline library. And, well, it's not done, but it's getting there. And it's quite significant using all kinds of functionality in the frameworks. And the interoperability is no big deal. So with that, have a look at the library. It's on GitHub. You can install it as usual, and have a play. Write your own applications in Haskell. Thank you very much.
Okay, go ahead.
So you're talking about scaling. Because initially, so in the first story, the middle part of the talk, I was thinking, well, a lot of this code looks rather like the sort of code that you and I used to write with C2HS, the sort of code that you find in the GTK binding. So talking about scaling, are you imagining that then people do not have to write a binding because they just basically write the bits of the binding they need as they're hacking their application? Or that we can now make binding so much quicker and easier because, which way do you see it?
Exactly what you said in the first point. The idea here was to get rid of binding libraries. I think binding libraries are holding us back. They're good for simple standard things like POSIX API, but I think for big frameworks they're not suitable because they're huge, they require a lot of maintenance, and the native libraries move so much faster than what we can track that as long as we are stuck with having bridging libraries for large frameworks, we are not going to get there. So the idea here is you use what you need, and you call on a use-by-use basis. And in what I found, in many of the cases, I don't just call one foreign function. I usually call a block of foreign function calls, which makes a lot of API calls to the framework. So in a way, the way you can see it is, in my application, what I've been forced to do in the past is, here's the framework, and the framework API is exactly where I have to put the Haskell versus, in this case, Objective-C interface. I'm forced, the interface is forced on me, and it's usually not a good abstraction for Haskell, right? So the capability I get here, I can have an application-specific slice somewhere in my application where while I write the application, decide where I want to put the abstractions. And if the library changes, new versions and so on, I can just use the host languages mechanism, CPP in this case, to do all the normal versioning stuff. Everybody else who codes Objective-C does as well.
Now, that's an interesting and fundamental difference compared to, even if we can automatically generate bindings, if
yeah.
you click a button and it generates the binding,
yeah.
That's still a difference.
Yeah.
That's very interesting, thank you.
Yeah, thanks.
Go ahead, Sam.
So I think I'm going to ask different questions than what I thought I was going to ask. But so, does this mean you're giving up on the idea of saying that we can write GUI applications in Haskell? Now you have to know Cocoa and you have to know Objective-C.
I'm not giving up on it. I'm just being realistic. Because what do I mean by that? We have been fooling ourselves, right? I mean, look at GTK. There's a lot of work went into GTK. And in GTK, it's actually quite nice because GTK, Haskell, provides a documentation which kind of transliterates a little bit from the C API. But generally, in order to write a GTK application, well, you have to know GTK. If you buy a book on GTK, well, it's going to describe the C API, and so on. For Cocoa, well, do we want to rewrite all the Cocoa documentation in Haskell? It's never going to happen. So it's inevitable that the person who codes against a large foreign framework has to understand the foreign framework in its own terms, if only for the documentation. So it's really only a question of syntax. The question is, are we going to write Objective-C calls in Haskell syntax so that we can kind of still make use of the documentation, or do we just say, well, let's write this in Objective-C? I think the knowledge you need about the foreign framework is about the same.
So what are your plans when your son wants to program GUIs? Does he have to learn Objective-C?
So at the moment I'm using gloss. I'm dodging this. And we'll do that for a while, and once he's a little older, I will have to introduce him to the evil side of the programming.
Swift will you mature?
Yeah. So the big picture here is, of course, that since I wrote this talk, Apple has brought out Swift, and now we want language inline Swift, and it's going to happen. Don't worry.
Go ahead.
Now, what would happen if the library that we're binding to, right, does add some extra parameters and stuff, and I don't notice or whatever, and then all of a sudden I try to compile again? At what point would it break, and how would I understand that break compared to maybe some other solutions?
So with other solutions, when you do cabal install Cocoa, it'll break. The cabal build will break. You in a code base you don't know, you don't understand, and then you have to write an email to the maintainer who is currently writing a paper and doesn't respond to you, and that's it. In this case, you get an error message by the Objective-C compiler in your own code, and it will be the same error message that every other Objective-C developer gets. So if you paste it into Stack Overflow, you'll get a reasonable answer.
That's fantastic. Thank you.
I mean, how do you debug this problem?
Okay, thank you, Manuel. So we're all